Right. Um, in the absence of questions, I will get started. Okay, so we have been talking about vector bundles, and last class we focused on how to build new vector bundles from existing vector bundles, and here's the principal constructions that we had, just to remind you. Um, uh, oops, here for a second. There we go. Um, so we had the notion of a subbundle. Okay, so if you have it's a subset F of a vector bundle E. Okay, so we have a vector bundle E. Okay, and we built a subbundle F, and this was a subbundle over M. Okay, and basically it's defined by choosing in a suitable way at every point a subspace of the fiber at E, which we called the fiber of F. Okay, then we had a product of vector bundles. So if I have two vector bundles, I can form their product, and I showed or argued at least that that was a vector bundle in a natural way. Um, and we took a sum of vector bundles. So in this case, so in this case, we allowed when we took the product, we allowed the vector bundles to be vector bundles over a different base. Here we have vector bundles over the same base, and we defined this thing which we called the Whitney sum. And the idea is the fibers here are the direct sums or the sums of the fibers of E and the fibers of F. Okay, and so the thing to proving that each of these things is a vector bundle is to verify that it satisfies the construction that you need for a vector bundle, which is a vector bundle structure defined by an atlas of vector bundle charts whose overlap maps are local vector bundle isomorphisms. Okay, so in all cases, to show something's a vector bundle, that's what you have to do. Then we had this sort of more complicated construction of a pullback bundle. And I'll give another example. I gave a bunch of examples of pullback bundles last time. I'll give another one just in a few minutes, which again will help you maybe understand this kind of abstract construction we had last time of a pullback bundle. But the idea is that you have a vector bundle over some with a base space being some manifold n, and then you have a mapping, and everything, these mappings and these vector bundles are all CR for some suitable R. Um, and a mapping which takes values in the base space here. And so the idea is that you take the vector bundle, which is over n, and you pull the fibers back from n to m. Okay, and that's the idea of the pullback bundle. All right. Um, so like I said, let me just give you another sort of elementary example of a pullback bundle. Um, So suppose I have a vector bundle over M. And now let um, S be a submanifold. Okay, then I have this thing which I can call the restricted bundle. Okay, so denote high, sorry, E restricted to S to be pi inverse of S. Okay. Um, So this thing, excuse me. So remember that when I go pi inverse, the idea is that it takes fibers over all the points in whatever the thing is you're pi inversing here, and the thing you're pi inversing here is S. Okay. And so here I'm taking the restriction to simply be the subset of E consisting of all fibers over points in S. And what would you like to be true? Well, you would like to be true that this thing is a vector bundle over S. Okay. Okay. And denote um, pi S to be uh, pi restricted to um, um, E over S. Okay. Then one can show that pi S, okay, maps now the restricted bundle. Okay. Um, and so what's this thing going to map to? Well, it's going to take points in E, which map to S under the projection. And so therefore this thing is really going to be, it's going to be M valued, but it's going to take its values in S. Okay, so this thing is really a mapping over S. Okay, is a CR vector bundle. Okay, so I'm not going to prove that. It's really tedious with charts, but quite elementary. So the idea um, is that you take a point in S, okay, which is also, of course, a point in oh, sorry, M, okay. So I take a point in S, which is also therefore a point in M. Then I take a vector bundle chart for E. About that point in S, which is also a point in M. Um, and every vector bundle chart gives you, because the base space M is a submanifold of E, the vector bundle chart defines for you also a chart for M, and it just turns out to be the submanifold chart corresponding to the vector bundle chart. Okay. And then you can change the vector bundle chart, the chart that is you get for M to be also a submanifold chart for S. Okay. And then, you have to define the vector bundle structure for this thing and show that the overlap conditions are satisfied. And it's not interesting or difficult, but it's tedious. All right. But for the purposes of the discussion here, I want to just make the following observation. Okay, is that use the not ancient English spelling. Um, uh, um, Moreover, this vector bundle is isomorphic as a vector bundle to the pullback bundle. Okay, so to the pullback of this vector bundle by the inclusion of S into M. Okay, so iota star S phi mapping to iota star SE going to S, where iota iota S is the inclusion. All right, so again, I'm not going to prove this statement, but I'll argue that it makes sense. Okay, so recall what the pullback is, that iota star S E. Okay, so the definition of this thing is that it is the set of points. Sorry, let me make sure I get the order the same as I had last time. Right. Okay. Okay, so it's the set of points x um, E in S cross E such that, all right, pi of E is equal to iota S of X. Right? That's the definition of this set. Okay, which is, the which is the total space for this vector bundle. All right, so let's see what this space means. Um, so so excuse me, what we're going to do is we're going to take points here, x and and E should have the property that it projects to the inclusion of x into E. And so really what this means is that the point E is in the fiber over the point x in S. Okay, and so you can just see just by the by construction. So we see easily, and by easily I mean just directly, that um, there is a bijection at least. I don't know anything about the bijection necessarily, but at least there's a bijection from iota star SE to pi inverse of S, right? By the argument that I just made. Right? So every point in here consists of points in here, which lie over um, base points in the submanifold S, and that's exactly what this thing is. Okay. And so again, I'm not going to prove that this vector bundle is isomorphic to this vector bundle, but this argument that it's just, well, this chatting that I'm doing here, at least I hope makes it seem like it's reasonable. Okay. Okay, so that's everything I'm going to say about this section. Now we'll move on to something else, still talking about vector bundles, and that'll finish our discussion of vector bundles. I'll talk about sections of vector bundles. Okay, so I have a vector bundle. Okay, so a section. All right, so let's say the section is CR also. So sometimes I'm slightly more flexible about this. So I'll say that the object itself, okay, which is the vector bundle, is of class CR. And then maybe I'll, if you have two CR manifolds, M and N, these are CR. Okay. And then you can have a mapping between them, which is, sorry, CK. Okay. And where K is less than or equal to R, because any CR manifold is obviously also a CK manifold. So sometimes in the course text you'll see that I'm a little bit, I'll say a CR vector bundle with CK sections where K is less than or equal to R. But for the purposes of the discussion in the lecture, I'll simplify things and just only consider the case where the geometric object and then the mappings that I'm considering are the same, or have the same regularity. Okay, good. So anyway, a CR section of E is a mapping. Which I'll denote by Xi. Okay, and it satisfies that pi C is equal to the identity map on M. Okay, so that's the definition of what a section is. So what does this definition mean functionally? So Xi takes a point M and maps it to E, right? And then the projection sends it right back. Okay, and so what it says is that it the projection sends me back to the same point I started with. So what this means functionally is that a CR section takes a point in M and maps me to the fiber over that point. Okay. That's the sort of maybe more slightly geometric way of thinking about what the definition is. Okay. All right. So sections are important, and we're not going to do much with them here except sort of basic constructions, and a little bit later on. Yeah, I don't know how much time I'm going to have. I'm going to have to strategize about how I'm going to finish off the course, uh, but I hope a little bit later on we'll talk about a special kind of section called a vector field, and vector fields are quite important. So hopefully you'll be able to talk about those in a slightly organized way. Okay, but um, suppose we have a vector bundle in a section and a chart. Okay, so it's going to be a vector bundle chart. Okay, so vector bundle charts are of the form V psi. Okay, so the domain is an open subset of E. Psi is the mapping. And then vector bundle charts, you'll remember, take values in a product like this. Okay. So as I've said, as I chatted about up here when I talked about how you make this thing into a vector bundle, I told you, and we've talked about it several times now, that if you have a vector bundle chart for E, this induces in a natural way a vector bundle chart for M. Okay. Um, and so I'll give that if I said there's a vector bundle chart for M, then that was a mistake. I have a feeling I might have said that. So the vector bundle chart for E induces a chart for M. Okay. Um, and I'll give that chart some notation. U phi phi. And then I'll call the chart codomain V phi, but the chart codomain is actually the same thing as this. Okay, so that's actually V psi 0. Be the induced chart. Then, okay, the local representative of C is C phi psi. Okay, so right, so C is a mapping from M to E, and I have this chart for M. And so sorry, I should say be clear here for M. Okay. And I have this chart for M and this chart for E, right? So this is the local representative of those for those charts. Okay, so this is going to take a point X and it's going to map it to a point X. Um, and I'll call this thing C psi of X. Okay, so this is going to be a point in V of U phi cross V psi 1. Okay. For some CR mapping C psi going from phi of u phi to v psi 1. Okay, and this mapping, and so I'll name this mapping while I'm writing down the proposition that characterizes it. This thing is called the principal part of C. In the chart. V psi, V psi 0 cross V psi 1. Okay. And the proof is direct, but I'll do it anyway. So first, note that C of U phi isn't, so in order for me to define a local representative of a mapping, the mapping needs to map the chart of the domain into the chart of the codomain, right? So that means here that I must have this, okay? Right, in order for the local representative to even be defined. But that's true, just because the points here are the points in the base space for this vector bundle chart, okay? And C maps points in the base space to points in the fiber over that same point in the base space. So this is true. Okay, so then for okay, so let me not write then because that's not what I meant to say. The local representative of any mapping phi from M to E satisfying phi of U phi is contained in V psi is right, so it'll just be phi psi of x is going to be, let's say, phi 0 of x phi 1 of x for some mappings phi 0 and phi 1. Right, that's just what the local representative was going to look like, right? So that's a vacuous statement. It really just defines phi 0 and phi 1. Okay, but the condition that pi composed with C of x, well, maybe let me write it like this, means that the local representative for C has form. All right, and so the punchline is that because C takes points in M to the fiber over that same point, this thing is just going to be X. So in other words, phi 0 is the identity. Okay, and then phi 1, and so I can just name phi 1 to be phi psi. Okay. All right, so that's what sections locally look like. They locally look like they're really just defined by their principal part, because in the other component of the vector bundle chart, they're just the identity. Okay. All right, so examples. Right. Um, so okay, so every vector bundle has a particular section. So let's let pi e m be any vector bundle. Oh, so I should also, sorry, I okay, introduce some notation here. Um, Gamma r f of e is going to be the set of all CRF sections of E. Right, so that's the notation that you use, this gamma notation here. Okay, that's uh, not sure who first contrived that notation, but it's standard notation for the notion of a section. All right. Okay. Um, so the uh, section, okay, let me call it zeta E. Okay, so this is going to map M to E. Okay, and it's going to take a point X to the point 0x, which is the zero vector in the fiber over X. This is called the zero section. Okay, so there's multiple ways to think about the zero section. So because M is a submanifold of E, and what's the submanifold M of E? Well, it consists exactly by definition. We defined what the base space meant, and the definition of the base space was that it's all the points in E which are zero when you represent them in a local vector bundle chart. Okay, so I mean, right? So this is just immediately says that this mapping is really just the inclusion mapping of M into E. That's another way to think about what the zero section is. Okay. Sometimes one wishes to think, and sometimes one calls the zero section the submanifold of E, consisting of all of these points, which again is just the inclusion of M into E. And so there's all these various ways of talking about the zero section. Sometimes you think of it as being a section, sometimes you think of it as being a submanifold, sometimes you think about it as being the inclusion map, but they're all the same thing. Okay. And the only sort of interesting conclusion I'll draw from this, um, so this shows that the set of sections is not empty. There's always at least one section, namely the zero section. Right? All right, so now let's look at another example. Let M be a CR manifold. And let V OV be a locally convex space. Okay. So then we have, and we talked about this when we talked about examples of vector bundles. So we have the trivial vector bundle. um, pi from M cross. I think I often do it like this. So Vm, which is V cross M to M. Okay, and so of course, pi of Vx, of course, is x. It's projection onto the second factor. Okay, so we have this trivial vector bundle. So then a section of Vm is, by definition, it's a mapping C from M to V cross M. All right. Okay, so C of X, therefore, is going to look like C1 of X, C0 of X. Okay, just because it takes values in a product. Okay, and then the condition with pi C of X equals, okay, so if I project onto the second factor by my construction here, this is C0 of X, but by definition of a vector bundle, that's just X. Okay, so the point is that C0 of X, of course, must equal X. That's the section property. Okay, so therefore, this section, therefore, is really defined by this mapping C1, and the mapping C1 is really just a mapping from M into V. Okay, so the association of a section C to the mapping C1 means that sections of Vm are really just functions, V-valued functions on M. And so you have an isomorphism of the set of sections. Yeah. Okay. Vm. This really is just that. Okay. All right. Okay, so those are some elementary examples. Um, and so, if you want some interesting finite dimensional examples, I have some constructions in the course notes for you to look at. Right. Okay, so algebraic structure of the set of sections. All right. So we talked about algebraic structure of this set. Okay, so the set of vector valued mappings on a manifold. All right. And we saw that this space had multiple algebraic structures. So first of all, it was an F vector space. Okay. And then second, it was a module over the ring of CR functions on M. And this set has exactly those two structures as well, and they look exactly the same. So I'll just write them down. Okay. So it has a real vector space structure. Sorry, not real, F. Okay, so the F vector space structure is defined by addition and multiplication. So addition. Okay, so take two sections, C1, C2, and to add them, I need to tell you what they do to a point in X. And so what do I know? Let me just first explain why what I'm going to write down makes sense. So I know that both C2 and C1 map X into the fiber over X. Okay, so E sub X. Okay. So because I know that, and I know that this space, the fibers of a vector bundle, have the structure of a vector space, those can be added. Okay, so I can just go, oops, C1 of X plus C2 of X. Okay, and of course the same holds for scalar multiplication. This. Okay, so I use here I'm defining scalar multiplication in here, right? And here I'm using scalar multiplication in the fiber. Okay. All right. So all right. So we have this space of scalar valued functions, right? And I denote this by this. So in other words, this is just another way of writing this. Okay. And I previously had illustrated how this space has the structure of a ring. So it has, and in fact, not just a ring, but also an algebra. So it's an F algebra. So it has three structures. It has addition of functions, and you add them rather the same as this. It has multiplication of functions by a scalar, rather like this. And then it also has multiplication. There's a product defined between two elements here, say f and g, by doing the obvious thing. Fg, the product of f of g evaluated at x, is the product of f of x and g of x. So pointwise operations. Okay. All right. So that's a ring, and so this space then becomes a module over this ring. Okay. So there's a C, R, F, M. Module structure. Okay. And so that means that I need to be able to do addition, and the addition, of course, is done in exactly the same way here. And I need to multiply to define the module structure. I need to multiply sections by not just scalars, but functions. And you do that in the obvious way. So once you write down the thing you're trying to define, there's really only one definition for it. Okay. So the space of sections has some algebraic structure, and sometimes that can be important. All right. Good. So that's vector bundles. So I think what I want to do now is I want to talk about a very important example of a vector bundle, namely this thing called the tangent bundle. Okay. So we'll talk about the tangent bundle for a few minutes. Well, more than a few minutes. Okay. So the tangent bundle is a particular and important example of a vector bundle, right? So one builds the tangent bundle in stages. Okay. And the first stage is to define what's called a tangent vector. Okay. Um, we'd start with a manifold, right? And of course, here I'm going to ask that R be strictly positive for reasons which we'll see in a second. Fix a point. Okay, so first, so a few simple definitions. So the first definition is uh, an F curve at x naught. Okay, so it's a mapping, and so um, uh, um, a curve, you normally think of a curve as being, you know, thing like that. Okay, but because we want to work with F here, we're going to talk about curves. Um, we're going to talk about complex curves as well as real curves. And so normally complex curves take as their domain, sorry, real curves take as their domain an interval. Okay, so what's the complex analog of an interval? Well, it's not so exactly clear what the correct analog of an interval is for functions which have as their domain a subset of the complexes. But what we're going to take is we're going to take a connected open subset. Okay, so it's a mapping gamma. Okay, um, and that's a let me see. Maybe I'll write my script I's like this, so they maybe a little bit more I looking. That's a an I into M, where this thing I in F is a connected open set. Okay. Um, with which contains 0. And moreover, gamma of 0 is equal to x naught. Okay, and so you should have some regularity on the mapping, and the regularity that I'm going to ask for here is C1. Okay. So in the real case, so I is a connected open set. So what that means in the real case is that I is an open interval, which has 0 inside it. And at time 0, it maps to x naught. So in the real case, the picture you can have in your mind is x naught and my interval like this, and then gamma and 0. Okay, and so gamma. Right, so it's a curve which passes through x naught at time 0 is how you can think about that in the real case. And in the complex case, well, however you want to think about that. Okay, so that's what a curve at f naught is. Um, so now the important thing here is to say what it means for two curves to be equivalent. So I have two of these curves are equivalent. if, okay, for any chart, u v v v phi about x naught, we have, okay, so phi composed with gamma 1. Okay, so phi composed with gamma 1 is now going to be a mapping from I1. Okay, so gamma is going to map it from I1 into M, and then phi is going to map it from M, or, U phi, into V phi. And so this gamma composed with phi 1 is a curve in V phi. Okay, the point is that it's a curve in a locally convex space, and so it makes sense to do that. I can take its prime. Okay, so it's normal derivative. Okay, at 0, um, and I can do the same thing for the second curve. Okay, so that's the definition of equivalence of curves. So there's a nice picture that goes along with this, and I'll draw that picture. Okay, so a tangent vector at x naught is an equivalence class of curves under this notion of equivalence. We may note a tangent vector. Okay. Gamma. So it's the tangent vector at x naught. Okay. So what's the picture that goes along with this? All right, so I have my manifold, and so I have been drawing manifolds like this, although this isn't a really awesome representation of a manifold in the general case, but for our purposes here, it's just fine. All right, so I have my point x naught, and I'm going to choose a chart, u phi, which maps into v phi, and then I have my intervals. Um, I1 and I2. Okay, so I have some curve, gamma. Okay, so here's um, I, let's say, and here's 0. Then I have this curve gamma. Okay, and then here I have phi of u phi. Okay, and then here I have phi of x naught. Okay, so my curve maybe looks something like that, whatever the curve looks like in u phi. And then down here, that curve is going to look like whatever it's going to look like. All right. But the thing I'm interested in is that. Okay. Um, and down in this picture here, this thing kind of makes sense because this curve here is the curve phi composed with gamma. Okay, and I can take the derivative of that thing at t equals 0, and t may be complex. Okay, and the idea is that you think of this as being the tangent vector to the curve at that point. So in your first multivariable calculus course, that's how you think about the derivative of a curve as being a tangent vector. So it's like the velocity as you along the curve as you pass through this point. Okay, so I can draw this thing, and here it even makes sense. Okay, so this thing here is phi. Sorry, I've run myself out of space. All right, so this is phi composed with gamma prime at 0. Okay, you can think of that as being a vector, which is intuitively um, intuitively the velocity along the curve as I pass through that point. And then the point is that up here, and so I'm going to now draw something which really doesn't make sense, but the intuition is that this up here is going to be the tangent vector. Okay. And so the idea is that, you know, in this picture, the intuition is you think of this thing as being the velocity of the curve as I pass through this point x naught, but it really only makes sense in any kind of literal way when you represent it. And sorry, I lost my chart here. Okay, it only literally possibly makes sense when you represent it in a coordinate chart. Okay. And then it's this thing, which is an actual thing. This thing is really just an equivalence class. And so the idea is that if you choose two different curves, okay, and maybe, I choose some other curve which passes through this point and maybe looks completely different, but as long as it passes through this point with the same velocity, and what that means by definition is that it passes through this point down here with the same velocity, then I call those curves equivalent, and the corresponding equivalence class is the tangent vector. Okay, and so the problem here is that this notion of a tangent vector that you're familiar with from vector calculus doesn't make sense on the manifold. It only makes sense in a chart. Okay, and so everything's being represented in a chart, and then you represent it here by introducing this notion of an equivalence class. Okay, so it's kind of an abstract construction of a tangent vector, but the intuition that you have in this sort of part of the diagram is exactly what you think. Okay, so it's really just an abstraction of the intuition that you already have about what a tangent vector means. Okay, good. Um, um, First thing I should do is in this definition of equivalence. Okay, I said for any chart, I should have this. All right. Um, and again, you have this thing that you might have with charts, which is that if you choose a chart and maybe you find that this is true in the chart that you chose, and I choose a different chart and I find that that's actually not true. Okay, so you have to eliminate that possibility. Um, so this is easy. So I'll not write a super careful version of this. I'll just say equivalence is independent of chart. All right, so this is a mnemonic for an actual statement, and my proof will be a mnemonic for an actual proof. Okay, and so if you have two curves, at x naught, okay, f curves, and let's suppose they satisfy phi composed with gamma 1 prime at 0 is equal to phi composed with gamma 2 prime at 0. Okay, so that's the equivalence condition in the chart phi, right? So satisfy this for some chart u phi, phi, v phi, v phi. Okay, and so what I want to do is I want to say that if this relation holds in some chart, then it'll hold in any other chart. Okay, so let me introduce another chart. U psi, psi, v psi, v chart about x naught. Okay. All right, so then it's essentially what I want to do is I want to prove that this relation holds um, not just for phi, but for psi. Okay, so then psi composed with uh, gamma a, so a can be 1 or 2. All right. And so what's this? Well, let me rewrite this as uh, phi composed with phi inverse composed with, oh, sorry. Um, let's see. Let me get the order right here. Oh, sorry, I want to keep the phi on the outside. Apologies. Okay, so I'm going to write it like this. Psi composed with phi inverse composed with phi. Yes, yeah, of course, because I know that this holds, so that has to be on the far left. Okay, composed with gamma prime at 0. Okay, good. So then it's just a question of using the chain rule. Okay. Um, so this is, and so the composition I'm going to use here is that this is a composition of that with that. Okay. And so this is D psi composed with phi inverse. Okay. Evaluated at phi composed with gamma at 0. Okay. And then phi composed with gamma prime at 0. Okay. So that's just the chain rule applied to, again, the composition of this with that. Okay. Now, oh, sorry. Uh, yeah, that's right. Sorry. And so the point is that this thing here, I already, and I forgot my A's, sorry. So A, A, A. All right, and so what I want to do is I want to show that if these are equal, then for A equals 1 and 2, then these ones are also equal for A equals 1 and 2. Okay, and why is that true? That's true because this thing is a diffeomorphism. So since psi composed with phi inverse is a C, and now here's where I need the R is strictly positive. Okay, so since that's true, it must be true that that D psi composed with phi inverse. Okay. Um, let me write this a little bit. Okay. All right, so I have a mapping, which is mapping, let's say V goes to, and here V is in V phi. All right, so it maps to this evaluated at any point in phi of x. So x V, and this now is in V psi. Okay, so this mapping is a linear homeomorphism for any x in phi of ux. And so particularly, if I take the point x equals uh, um, phi composed with gamma at 0, okay, so and so particularly phi of x naught, okay, because of course gamma at 0 is equal to x naught, so this thing is really just phi of x naught, okay, and so therefore, okay, because this is just this linear homeomorphism, applied to that, okay? If this is true, okay, then it'll be true for the psi composed with gammas as well. Okay, so the punchline is that space phi composed with gamma 1 prime at 0 is equal to phi composed with gamma 2 prime at 0 implies that psi composed with gamma 1 prime at 0 is equal to psi composed with gamma 2 prime at 0. Okay, that's my chart independence. Okay, and it's just this standard argument where you insert the identity map. Okay. All right, good. Now, so that's kind of an elementary construction to show that equivalence is independent of chart. Now I'm going to do some constructions which are not so elementary. And I'm going to talk about tangent vectors as being what are called derivations. Okay. And so I'll introduce some kind of abstract definition here. Okay, so let M be a CR manifold. And so R has to be positive. X naught point in M. And F derivation. So this is kind of an algebraic construction. We won't really see the um, full power of these ideas until we talk about vector fields, which hopefully we'll be able to talk about this. Okay, at x naught is a mapping. I'll call it theta. And it maps the set of functions to f. Okay. And it has some properties. So it's linear. Okay, so we've already seen that this space has an algebra structure. So this notion of a derivation is a thing which you define on algebras. And this also is also an algebra. And so this is like a derivation of these two algebras. That's the idea. Okay, so what this means is that it's linear. So theta is f linear. okay, as a mapping of vector spaces. Um, and then it interacts with the product structure here. Okay, so I can take two functions and multiply them, and it interacts with that in a specific way. It interacts with that like product rule. Okay, so theta of fg, if I take two functions and multiply them, it's f of x naught theta of g plus theta of f g of x naught, right? So this is a product rule, right? So you fix f and you apply the derivation to g, and then you fix g and apply the derivation to f. Okay, so there's an evaluation at x naught that's happening here too. So that's why these are derivations at x naught. Okay, so what we're going to do is we're going to examine the relationship between tangent vectors and derivations at x naught. Okay. And the relationship is kind of complicated to develop, although the punchline of it is relatively simple. To actually prove everything requires a bit of effort, so that's what we're going to finish the lecture with today. Mm. Okay, so there's a list of statements that I'm going to give here. First is that so sorry, notation dir x naught of CR is the set of derivations at x naught. Yes, that's the notation I'm going to use for the set of derivations. So the first statement is that this is a vector space. Okay. So then what I'm going to do is I'm going to define a mapping from curves at x naught into derivations. And we'll see that essentially this mapping on curves only depends on the tangent vector associated to that curve. Okay, so given a curve gamma at x naught, okay, so what I'm going to do is I'm going to define a mapping from here to here. The same domain and codomain as derivations. Okay, so I'm going to call that mapping theta gamma. Okay, and so it's going to take a function f, and it's going to map it to f composed with gamma. Okay, so gamma is an F curve, right? So gamma maps F into M. Sorry, but maps, yes, a subset of F. So I have too many Fs going on. A subset of this F into M. And then little f maps M into big F. Okay, so this thing is just going to be a mapping from a subset, open subset of F into F. Okay, so the point is I can do this. Okay, and my claim is that this is an F derivation of x naught. Okay. So you can see here, I'm only taking the derivative at zero, right? So it's not hard to imagine that this expression here doesn't really depend on gamma except through the derivative of gamma at zero. Okay, so somehow you think of this expression as not being a mapping from curves. Okay, so it doesn't really depend on the curve, it only depends on the tangent vector of the curve at um, at, as it passes through x naught. Okay. All right. So the next statement. Oops. Um, there is a neighborhood O of x naught such that the mapping. Okay. All right. So this mapping, I'm going to write it as tau x naught, and it's going to map the tangent space. Right. So the set of tangent vectors. So t. Oh, I'm very sorry. Okay, I keep forgetting to introduce the terminology or the notation. Okay, so why are you doing that? Oh, interesting. Hmm, cool. Hmm, for some reason, it's forbidden that part of the screen. Okay, good. So T x naught m is the set of all tangent vectors. Okay, and this is what's called the tangent space. Okay. All right, so this introduces the notion of the tangent space. It's just a set of all tangent vectors at x naught. Okay. Um, and it's the structure of the set of the all tangent vectors at x naught that we're trying to understand here. Okay. Oh, that this set derivations at x naught of this. Okay, so what is this mapping? So this mapping takes a tangent vector, which by construction is an equivalence class of curves. Okay, and it maps it to this derivation associated with any curve gamma in the from the equivalence class. Okay, so mapping to theta gamma um, has the following properties. Okay, so the first property is this mapping is injective. Mhm. Its image is a vector subspace. Okay, and C for each chart. Okay, the mapping Oh, so apologies for each. I need some notation for the chart. U phi, phi, V phi. Okay. The mapping. Okay, so this is going to be a mapping from the vector space V phi. Okay. Um, and so I'm going to write something down here, and that's something that I'm going to write down requires a little bit of proof, so that'll be part of the proof. And this the I'm going to write any point in V phi as phi composed with gamma prime for some curve gamma at x naught. Okay. And so, an element of V is a vector, and what I'm really saying here is that every vector can be represented as the tangent vector of a suitable curve. So that's one of the things we have to prove. Okay. And this maps to tau x naught of gamma x naught. Okay. And this is the derivation. This mapping is linear. Okay. All right. And what we'll see um, is that this essentially gives us a way of defining a vector space structure on here. Okay, and the vector space structure is going to be the vector space structure that it inherits from sitting inside this vector space. Okay, so we have this mapping which injects this thing into here. Okay, and its image is a subspace, and this thing inherits a well-defined, and the well-definedness here will mean independent of chart, a well-defined vector. It inherits a well-defined vector space structure from its image. Okay, that's what we're proving here. Okay, proof. All right. So the proof is elementary, but requires a few tiny tricks. Okay. So first, the vectors. The part one is pretty immediate. I'll tell you what the vector space structure is. Okay. And then you have to verify that it satisfies the list of vector space axioms, but that's easy, as it usually is to verify those. Okay, so I take two derivations, theta 1 plus theta 2. Okay. All right, so I need to tell you how to add them. And these things, what do thetas do? Thetas take functions and give you scalars. Okay, so all I need to do to tell you what the vector space, what addition looks like, is I need to tell you what this thing does to a function. And of course, like all of these things, it does the obvious thing. Okay, and similarly, I multiply a derivation by a scalar, a, and I need to tell you what it does to an f, and it does the only thing that it can do in terms of the symbols that you're given. Notice you have to be a little careful with that argument of it. It does the only thing that makes sense because, for example, a derivation doesn't do that, right? The only thing that would make sense here would be that this is theta of f, theta of g, right? So, but that's not a derivation. So, I often say, once you write down this, this is the only possible definition, but you have to be careful with that kind of reasoning. Okay. Okay, so now let's show that given a curve, okay, this construction here defines a derivation. Okay. All right. So we're going to do that by working in a chart. Okay. Okay, so I have um, two kinds of things I'm talking about in this construction. One are functions, and then one is the curve. Okay, so let f phi from phi of u phi to f. Okay, that's going to be the local representative of the function. And also gamma phi is the curve. That's going to be the local representative of the curve. Um, okay, of f and gamma. Okay, so I'm assuming here, because I'm only interested in this construction, in differentiating this thing at zero. Okay, I've gone ahead and I've shrunk I to guarantee that gamma takes its values inside the chart domain. Okay. All right. Um, so Okay, so what are the local representatives? Well, the local representatives, remember that, so this is takes values in F. This takes values from F. Okay, and so the chart I'm going to be using for F is just the identity chart. And so the local representatives look like this is F composed with phi inverse. Okay, and gamma phi is phi composed with gamma. Okay, so that's what those local representatives look like. And so there seems to be a piece missing from the local representative, namely a piece here and a piece here. But those are just the identity map because I'm working with F and I. Okay. All right, so I know that that's true. Okay, that's nice. Um, All right, so now let's understand what this mapping is. Okay, so this is my mapping. It sends a function to this thing. All right. Okay, so note that f composed with gamma prime at 0 is d. Again, just now I'm just going to use the chain rule. So d f phi at uh, gamma phi of 0 gamma phi prime at 0. All right. um, yeah. Okay, good. All right, so what do I need to do? I need to show that I need to show the derivation property. Okay, so to show the derivation property, we need to show that again, theta of fg is f of x naught theta of g plus theta of f g of x naught, right? That's the derivation property. And the point is that this relationship means that it suffices to prove this, not for manifolds. It suffices to prove this for open subsets of locally convex spaces. Okay, so without loss of generality, we assume that M is O is an open subset of a locally convex space V. Okay. All right, so I will now advise you that I'm going to go over time here. All right. Um, because I want to finish the proof of this, and it'll take a little bit of time, but so I'll probably be 15 minutes over. But I finished early some days, so my guilt level is bounded from above by a pretty small number. Okay. Okay, so what I will do is I'm going to um, think about what I'm going to be using here, what the definition of the derivative is, okay? Namely that it's the directional derivative, okay? So note that uh, okay, given um, v, oh, okay, so sorry, not note that. Let's define. Okay, so I have this thing here, and I'm just going to call that V. So denote V to be gamma prime phi at 0. Okay, so and also and okay, so my expression here for um, um, this derivation depends on gamma, okay? But as I've said a few times already, this only depends on um, gamma prime at 0, okay? So in other words, it really only depends on V, okay? And denote just because I want to just replace the dependence on gamma with just dependence on V because that's really what it is. Okay, so replace theta gamma with um, theta V. Okay, so then we need to show that theta V of FG is the usual thing. So f of x naught, theta of G plus theta of F, G of x naught. Okay. And what's theta of V? So theta of V. Okay. All right. So again, I'm replacing theta gamma with theta V. And so this is going to be a mapping from CRF of O into F. And it's going to send a function F to df of x naught V. And why is that the right thing to do? That's the right thing to do because of this formula. Okay, so now what I'm doing is I'm just replacing everything on M with the corresponding thing in a locally convex space. Okay, so theta gamma gets, okay, which is just that, okay, gets replaced with theta V, which is this. Okay, so it makes it so that I can just do elementary calculus is the point. Okay, all right, so I need to prove this. But that's relatively easy at this point because, again, this is just going to be calculus. All right, so then theta V, um, theta V of FG. Okay, so by definition, it's d FG at x naught V. That's its definition. Okay. And by definition of D, this is the limit as t goes to 0 of, okay, so it's going to be f of x naught plus tv, g of x naught plus tv minus f of x naught, g of x naught over t. Okay, that's the definition of d, the directional derivative. Okay, but now I know that this function as a function, so the whole point of taking directional derivatives is that you now are working just with things which depend on a single variable, namely the variable t. Um, and I know that functions of a single variable satisfy the product rule. Okay, so this is um, um, df of x naught. Okay, so now I'm just using the normal product rule. V um, plus, sorry, g of x naught plus f of x naught dg of x naught v. Okay, product rule. Okay, and so notice this really is the product rule from first year calculus, right? And the reason is that this is a scalar function, okay, because f and g just take values in f, a scalar function of a scalar variable, right? So it's literally just the ordinary product rule. There's nothing fancy there at all, okay? And so that proves that this thing is a derivation, okay? Good. Now, part three. See? So part three is kind of the interesting part, and that's going to take me a few minutes. Okay, so again, I'm going to work in a chart, okay? And so what's part three? So part three says I have this mapping from the set of all tangent vectors, the tangent space, into the space of derivations. Okay, and what does this thing do? It takes an equivalence class of curves with a representative gamma, and it maps it to this derivation from part two, theta of gamma. Okay, and I'm going to show that for in some neighborhood of x naught, it has these three properties. Okay. Okay, so I take a chart. Sorry, be a chart. And that, so I'm going to take O, which is essentially what I did in the previous part of the proof too. I take O to be the chart domain. Okay, so basically I'm going to be working in a chart. Okay, so first I'm going to prove injectivity. Okay. Okay, so I need to show that if I have two, right, so the domain of this mapping is the set of all tangent vectors. So I'm going to take two tangent vectors which differ, okay, and I'm going to show that their derivations differ. Okay, that's the idea. Okay, so let gamma A from I um, A into O be F curves at x naught. That are different, which means that phi goes with gamma 1 prime at 0 is not equal to phi composed with gamma 2 prime at 0. Okay, so the equivalence classes that they define are different. Okay, so by the Hahn-Banach theorem, which we didn't talk about in detail. And if you have no idea what the Hahn-Banach theorem means, Well, it means lots of different things. What I'm going to do here is I'm going to use it in the guise of if I have two vectors in my vector space, which are different, like these two, okay, then I can find an element of the dual which differs when you apply it to those. That's one of the consequences of some version of the Hahn-Banach theorem, right? So the Hahn-Banach theorem comes in many different flavors. All right, so by the Hahn-Banach theorem, let lambda be in the topological dual be such that um, lambda of phi composed with gamma 1 prime of 0 is not equal to lambda at phi composed with gamma 2 prime at 0. Okay. All right, so now define f. Okay, so f is going to be a function on my chart domain O. Okay, so this is going to be, in fact, it's going to be C infinity, so it'll be particularly, it'll be a plus CR. Okay. Okay, so f is going to be defined essentially by lambda. So f at a point x, okay, so x is going to be a point in my chart domain. And to define f, I'm going to apply lambda to the image of x under phi. Okay, so it's going to be lambda composed with phi of x, like that. Okay. Okay, so then, okay, so what I'm going to do is I'm going to show that for this f, um, theta gamma 1 applied to this f is different from theta gamma 2 applied to this f. Okay, so again, let me remind you what's going on here. Okay, so I have two equivalence classes of curves defined by gamma 1 and gamma 2 that are different, and I need to show that their derivations are different. Okay, so that means I need to show that according to this definition of theta gamma 1 applied to f is different from theta gamma 2 applied to f. Right? So that's what I need to do to show injectivity. Okay, so then, all right, um, theta gamma 1 of f. Okay, so the definition of theta is that this is actually, um, so the definition is that this is f, sorry, sneeze. Okay, so f composed with gamma 1 prime at 0. That's the definition of theta gamma 1. Okay, now I'm going to use the definition of f. So this is lambda composed with phi composed with um, gamma, sorry, 1 prime at 0, right? That's the definition of f. Okay, and all right, so lambda here is a continuous linear function. And so I'm going to apply the chain rule, and I'm going to apply it to lambda and its composition with this composition. All right, and so I know that the derivative of lambda is lambda. Okay, so when I do this derivative, I get lambda applied to theta composed with phi composed with gamma 1 at 0. And let me be clear here, like that. Okay. And so I know that this is different from that. Okay. And so this is not equal to lambda phi composed with gamma 1 prime at 0. Okay. And so this is equal to theta gamma 2. of F. Okay, so this shows that um, the mapping tau x naught is injective. Okay, great. Okay, so now part B. So I'm really going to do parts B and C together. Okay, um, and I'm going to do it. I'm going to not. I'm going to prove something which has parts B and C as a consequence. Okay. Okay, so the first thing that we'll do is we're going to. So I told you when I wrote down this construction um, that there's a thing here that has to be proved, namely that every vector in V phi can be written like this for a suitable gamma. Um, that's kind of obvious, but I'll do it anyway. So note that if V is in V phi, um, sorry, is in so if I have a so let me okay, so let me do it this way. So first I'm going to claim that the mapping um, which maps the tangent space T x naught M into um, V phi is a bijection. Okay. So that means I need to show that it's surjective and injective. So injectivity is obvious by the definition of equivalence class, right? So if I take two different curves whose image is the same, that means they're equivalent, and so therefore they must have been the same in the same equivalence class to start out with. Okay, so it's really just surjectivity that I need to worry about. So injectivity is clear. By equivalence. Okay, so to show surjectivity, let V be in V phi and note that if gamma of T is phi inverse of phi of x naught plus TV. Okay. So what am I doing here? I'm taking the curve which passes through phi of x naught at time 0 in the direction of v. So this is like a straight line curve. Okay, and this curve is in v phi. And then I'm just taking its mapping under the inverse of the chart domain to give me a curve gamma. Okay, so if I define gamma like this, then um, um, phi composed with gamma prime at 0 is obviously equal to v, right? If I just apply phi to both sides of this equation, it cancels that one, and then I take the derivative of this mapping at t equals 0, and that's just going to be v. Okay, so that shows surjectivity. Okay, good. So what I've done now is I can replace Tx, the tangent space at x naught, with v phi. Okay. Okay. Um, so, okay. All right. So now, um, we will show that. Okay. Um, the mapping. Okay. All right. So what's the mapping that I have here? So I have uh, what I have here is I have this one here. Okay, and I choose an arbitrary tangent vector in here. And so the point is that I've shown that this is possible for some curve gamma. Okay, and I need to show that if I apply this mapping, all right, so I have this one from up here, which assigns to a tangent vector the corresponding derivation. Okay, I need to show that it's linear. Okay, good. So, all right. So this is, again, this is not a difficult construction, um, um, but it requires a bit of notation. Okay. Um, all right. So the mapping B phi. Let me just sort of rewrite the mapping here. Okay, so it's going to be um, phi composed with gamma prime 0 maps to tau x naught of gamma x naught in. Okay, and remember that this thing is theta gamma, okay, is in here. Okay, and you show that that thing um, is linear. Okay, all right. Okay, so let's look at additivity. Okay, so first of all, let me introduce some notation. So, and the notation here is really coming from here. Okay, so let V be in V phi and denote gamma V of t to be phi inverse of phi of x naught plus tv. Right, that's um, this curve that I used up here. Right. Okay, so now, I need to show additivity, so I need to take two vectors here, v1 and v2, and I need to consider the curve gamma sub v1 plus v2. Okay, so that's kind of an annoying thing to consider, but that's the thing I have to work with. Okay, so let's do that. So let's let F, capital F of S and T B. Okay, so it's going to be F um, um, sorry, I also need an F, so I'm going to fix an F. So let F be in C R F of O, because I'm going to show linearity applied to F. All right, so I need to fix an F. Okay, and denote capital F of S and T is going to be F phi. Okay, so the local representative of F at phi of x naught plus S v1 plus T v2. Okay, so it's a function of two variables. And I'm also going to write delta of t to be uh, t t. Okay, and why do I denote these two symbols? Note that f composed with delta of t is f. Okay, so f composed with gamma v1 plus v2. Right, so that's what all this stuff is about. Right, so if I said s equal to t, okay, and I look at my definition of gamma v, which was here, okay, then I can see immediately that this, and by definition of capital F, this is f phi, and this is gamma phi, okay, and I've already seen previously that f phi composed with gamma phi is the same thing as f composed with gamma. All right, so that's where I get this from. Okay, good. The point is now we've reduced it to a calculation. Okay, so then tau x naught applied to the equivalence class of gamma v1 plus v2. And what you want to show is that this is going to be tau of gamma v1 plus tau of gamma v2. That's where you want to end up. Okay. Okay, so this is, by definition of tau, this is theta uh, um, gamma V1 plus gamma, sorry, V1 plus V2, V2 applied to F. Okay, that's the definition of tau. Now you apply the definition of theta. The definition of theta is that this is d by dt at t equals 0 of f composed with gamma v1 plus v2 of t. Right, right? So right, that was the definition of theta. Okay, so now we note that this, or sorry, this is that. Okay, so this is d by dt at t equals 0 of f, capital F, um, composed with delta, sorry, delta of t. All right. Okay, so now I'm going to use the chain rule on this composition. So this is df at delta of t, delta, sorry, at t equals 0. Delta prime at 0. Okay. Now I use the product rule. Okay, I use the product rule on f because f is a function of two variables, so I'm going to differentiate it in the first variable and then the second variable. Okay, so this is d1 f at, okay, delta of 0, but delta of 0, let me stick that in. That's 0 comma 0, right? That's the definition of delta up there somewhere. Yeah, here. Okay. And then delta prime at 0 is equal to 1. Okay. Plus d2f at 0, 0, 1. Okay. All right, right. So 0, 0 is just that, and this is 1. So that's delta prime. Okay. So now I use the definition of f. Okay, and so I'm D1f means I'm differentiating with respect to the first argument, which is s, and holding t fixed. Okay, so what you get here, I'm sorry, is you get d f phi of um, uh, so f at 0, 0, but f at 0, 0 is phi of x naught, and then v1 plus d f phi at phi of x naught v2. Okay, so this is the symbols, because I don't have everything on the screen here all at once. The symbols look more mysterious than they are, but the transition from here to here is just a straightforward application of this formula, and you calculate its derivative using the partial derivatives. Okay. All right, so now I see why I did this. So this is theta gamma v1 of f plus theta gamma v2 of f. Okay. And so therefore, this is tau x naught of uh, gamma v1 x naught plus tau x naught um, gamma v2 uh, x naught. All right, so that's linearity. Okay. All right. Okay, so that's how you prove linearity with respect to addition, and the same kind of construction holds for scalar multiplication. So the same idea shows that tau x naught of gamma a v is equal to a tau x naught of gamma v, like that. Okay. All right, so that's as I said, that's not it's not a hard construction, but it's I guess a little bit of a trick. Okay. Um, and so that shows that this, okay, so that shows that this mapping is indeed linear. Okay. All right, so I will stop there for now because I've gone way over time, and but there will be some important discussion of this next time. Okay, so that finishes the proof of the basic ideas here, but the most important thing is discussing the meaning of these ideas, and that's one of the things that we'll talk about next time. Okay, so next time is going to be discussion of this result and other stuff, of course. Okay, so unless there's questions, that'll be it for today. Okay, I'll see you in 2 days.